about porting Go. We'll look a little bit at Go internals and how we ported Go to Solaris. Right, so I worked on some kernels, the Solaris kernel. Also did a little bit of Windows kernel stuff. Of course, I like Go. So I suppose most people will not have the opportunity to port Go in general because there are only so many platforms to port it to. But the knowledge you get by doing this, I think, is very valuable, and I think it's interesting. So yeah, sure. Why shouldn't you port Go? I mean, monoculture is bad. So if Go is ported to as many platforms as possible, it can only be good for Go. So as I was saying, porting Go gives you a massive learning opportunity to learn about its internals, which is a very useful thing, even if you work at the higher level. I mean, you don't have to dive into the runtime and you can just use Go, but Go provides you with some abstractions. And I think it's very valuable to understand how these abstractions work, because I don't think that abstractions are black boxes. Abstractions are very useful because they allow you to work at some level that you like working in, but I think it's crucial to understand these abstractions in order to write software that can really understand the impact it has. You can really understand what it does at the operating system level. Right. Anyway, I think porting is also a way to improve Go. Various platforms exhibit various bugs or trigger various bugs. We found some bugs were doing the Solaris port, for example. Of course, personally, I did this port because I wanted to use dtrace on it, and dtrace works best in Solaris. There's a port of dtrace in FreeBSD. I guess it's a few years back behind Solaris, and there's a port in OS X as well, which started working. It was ported in 10.5. It worked reasonably well. Then it was kind of forgotten. Now it's starting to work well as well. But previously, dtrace on OS X was not very useful, I'd say. Also, there are lots of 32-bit embedded microcontrollers which you, in principle, could run Go on. Go won't work on 60-bit platforms, but there are lots of 32-bit microcontrollers, and you can make it work, I suppose. Also, I know some sysadmins like writing Go tools to simplify their life, and if you use a less used operating system, you're going to make your life better, I suppose. Of course, porting Go is extremely fun if you're into low-level things. So, we're going to take a look at how things are organized inside the Go tree, just to have a basic high-level overview. I mean, you need to know where everything is and where everything goes. So, of course, you probably know already. Okay. Of course, you know already where the this one. Of course, since you probably build Go from source, you'll know these things already. I think that only all.bash is documented. You need to be aware of make.bash primarily, because all.bash invokes make.bash part of this build process. And since you won't be able to run the tests and since you will want to cross-compile at all times, you will need to run make.bash, I suppose. So Dave Cheney wrote a nice description that explains how all this works, and I encourage you to read it and play with the tools. Basically, when you type make.bash, there's a very simple C program that gets built. It's the dist tool. You can find in here. There's a README. You should read it. The dist tool is a very simple C program. It's really portable. All the OS level stuff is concentrated in one file. It's very simple, so it can be built by just doing cc star.c, and it should build it correctly. It's really simple C, as I was saying. This does the initial bootstrap. It knows how to build some things, like it knows how to build the go tool. It knows how to build the runtime. This is useful because it also, I'll just show you, I suppose. Building the runtime, when building the runtime, there are some files which will be auto-generated. So you need to know how to use dist manually in order to auto-generate these files. Otherwise, pure Go packages are really easy to build using just the compiler, but you really want to use this you really want to use this actually. So, right. Of course, I assume you are already aware of build constraints and how different files get built. To recap, if a file ends in _Linux, it will only be built for Linux. You can also put this at the beginning of your file, and this is a better example, and then it will be built only for Linux or Darwin. This is useful because you have like portable Unix files that just disable Windows and Plan 9, and you put everything you want there. This is documented, so I won't insist on it much, and I suppose you already know this stuff. Eventually, CMD dist will build the Go tool, which you are already familiar with, and the Go tool can build everything else. And the Go tool is really interesting because it's essentially a cross-build tool. It always cross-compiles. So your Go tool runs on your machine, but it can produce binaries for everything else. You should really take a look at all these files and have a high level overview of how these things are organized, and try for once not running make.bash. Make.bash has a flag. I think it's only a dist only, or dist tool, I think, which will only build a dist tool. And you should try just using the dist tool manually to build the runtime, the Go tool, and then use the Go tool to get familiar with these things. Right, this is I just wanted to show you this, how Go is built, which I already talked already. So the dist tool is built. As you can see, it's trivial. This is the flag that I was talking about. So you can make it stop here. This is very useful because as you will be doing your port, things won't work. This will be the first thing that will work. So it's useful to be able to stop the process at this point. So if you take a look at this, you will see that essentially when you are cross-compiling, first you build a set of tools and packages for the local system in order to be able to compile the Go tool, which will run on the local system. And then you will build everything for your target operating system as well. One note, dist, I suppose I will talk about it later. Dist will build the Go tool. It builds a Go bootstrap binary. It's the regular Go tool with networking pulled out in order to dist knows internal details about packages. For example, the Go tool itself can do can infer dependencies between packages and things like that, but this cannot. So this has a list of things it needs to do, so it needs to be told what to build. And so, of course, we don't need networking to build Go Bootstrap, so networking has a lot of dependencies. So we just take that out. By the way, we use build tags to I think, to make this work. So, the compilers. The compilers are, they actually come from Inferno, and they come from Plan 9. They're very simple compilers. I mean, I think they're like 30,000 lines of code, I suppose. Currently, they're written in C. They will be, the Go compiler, I suppose, will be written in Go. There are some documents that describe the high-level structure of these tools, and you should read them. Mainly the Ken Thompson and paper, and Rob Pike also wrote a paper. These are very old, and details have changed, but they give you the necessary background to work on these things. Anyway, you won't be changing anything in the compilers, but you have to be somewhat aware of how things are organized. Of course, the Go compilers, there's no documents about those, but they work pretty much the same way. Yeah, so they are always cross compilers. They are again, currently these details will change. Each compiler generates code for one particular architecture, and the code does not depend, well, it used to not depend on the target operating system. This changed very recently, with still, I don't think it's a real dependency, but this will change because the parts of the linker will get integrated in the compiler. But the interesting thing, the thing you need to know is that they are always cross-compiled basically. And when I say they generate plain object files, it's not entirely true. I mean, it's things change. Things are in a state of flux always. So the compilers compile, the C compilers compile something that looks like C. There are some small extensions which are described in those papers, so I won't talk about them because they don't matter much. But one which is important is the extern register storage class. I will talk about this a little bit later. Originally, this storage class made variables which were extern register. They were in a per CPU register, so it wasn't global. It was per CPU, which was really important. Right now, the details are. I will talk about this a little bit later. Yeah, there are some plans how things are going to change, and I encourage you to read them. Provided a link. The assemblers are really simple programs. Until very recently, there was no document that described what's happening in Go. There is the original Plan 9 document, but it is quite obsolete. For example, I think it describes a different calling convention and a lot of stuff missing. But now we do have a guide. Again, I encourage you to read it. So the calling convention, the assemblers provide an abstraction of frame pointers, but in the actual code there are no real frame pointers. Everything is stack based. You passing on a stack. For Go, the return values are also on the stack. The C compilers return in AX. This is important when writing functions that are to be called, writing C functions that are to be called from Go or vice versa. This is just a quick overview. You should really read the document I mentioned earlier, and also you should play with these things because you will be doing assembly programming with them. Pack is just a variant of R. It packages object files into an archive, which the linker then uses. I mention it here because you will want to manually use pack in order to extract and insert your own symbols in the archives. The linkers, again, they are described to some degree in the compiler paper. They can generate different kind of binaries. For example, A out elf, of course, P. Yeah, somewhat surprisingly, the linkers implement. They do code generation. They do they do dead code elimination, for example, as an optimization, which is, I suppose, surprising. And they also implement split stacks. We will talk about how split stacks are implemented later once we know more about the runtime. But it's important to remember that the linkers will insert code inside whatever you write. Even if you write it in assembly, they will modify that code. So if you really need to know about the code that's actually running, the linker has a flag to dump the assembly. The compiler also has a flag, but as I was saying, the linker rewrites this stuff, so you need to be aware of this distinction. There's a document, I didn't reference it here, inside I think it's inside runtime, I think, that describes how CGO works. It's important to know how CGO works. Well, depending on operating system, it might or might not be important to know how CGO works. The important detail here is that some time ago, support was added for external linking. That means that the Go linker will link an elf, for example, object file, which will then be linked by the system linker. Why is this useful? ELF is very complex. It supports a wide range of relocations, and the Go linker doesn't know about all this stuff. So we defer the work to the system linker. Why I mention this right now is that you must always make sure that your port works both with the internal and the external linker. There's an external flag when calling the linker. I will mention a little bit about how external linking works later in this talk. So the Go runtime. The Go runtime implements a lot of things. Many we're not really interested in because they are very portable. For example, garbage collection. You probably don't have to do anything to the garbage collector. So I suppose I'd say half of the runtime code is portable, and it runs on top of things that are either architecture dependent or operating system dependent. For example, all the scheduling depends on what primitives your operating system exposes for doing scheduling stuff. yeah, I suppose it's very unsurprising that every Go program, the entry point is inside the runtime, because the runtime has to do a little bit of things. I suppose we could do this, I suppose. Right. So the actual entry point is depends on the operating system, because they need to get the arguments to the program, and that detail depends on the operating system. But so here is the real entry point, which we'll just call RT0 Go, which we'll take a look a bit later. Right now it's written in C assembly and Go as part of getting rid of C and making everything in Go. I suppose most C will get rewritten into Go, and some C will get rewritten into assembly, because you really need assembly in the end. So obviously the runtime has to do system calls. Go has regular programs have to do system calls as well, but this is implemented differently. The runtime must do some basic system calls, like for example the thread creation stuff, the synchronization, the signaling stuff, and for most platforms, the mechanism by which runtime and syscall are doing this are the same, but for some platforms are different. For example, in Windows and Solaris, it's quite different. Right, so because Go on most platforms does system calls manually without relying on libc or anything else, they are written in assembly. But of course, in Windows and Solaris, that ABI is not stable, so they need to do something else, which we will take a look later. Right. So when doing your port, you have to have some awareness of how scheduling works and how guarantees are multiplexes on threads. Daniel Morsing wrote something about this. You should read that. What's really important is that the runtime, each guarantee and each thread have an associated resource, which it's called a G and an M. M stands for machine. G stands, I suppose, for machine. G stands for guarantee. And many G's are multiplexed onto an M. Some, I think about a year ago, P's were introduced, so M's that run Go code have to acquire P's. That's when debugging, you should be aware of these things, but the most important thing that you should be aware of is how the runtime uses G and M specifically, and how the runtime accesses G and M. Details vary between platforms, of course. Right, so we'll skip this, I suppose. Yeah, you need to be aware that right now the runtime is not preemptive. There was some work that added more preemption points, but it's not preemptive. I mean, it's voluntary preemption. Of course, this can change any time. Right. Okay. So, Go uses segmented stacks, and you need to be aware of this for a few reasons. It usually means that when you're doing assembly or C, you really need to know if your function is able to split the stack or not. In practice, for GC, you have 120 bytes of stack available. If you really want to write a function that you are sure that will not split the stack. Just an example, in GCC, I think it's about 1K, so there's huge difference there. The way segmented stacks are implemented is that at each function entry, the function itself checks if it needs to if it needs a different stack segment, and of course that means that how can it know that it needs a new stack segment? So it does look inside G to look for the stack guard. So it uses G to look for the stack guard, and this way it can know if it needs to allocate a new stack segment or not. Stack guard is also used for forcing a new schedule event. I think there's a thread inside the runtime that checks if each coroutine exceeded its quantum, and then it can update the stack guard. So it will trigger this check, and this check then we'll see if it just wants to grow the stack or if it needs to be preempted. So this means that at each function entry it needs a way to find G, which depends on the system. So I was telling you earlier that the compiler produces code independent of the target operating system. So I suppose it was never really true, because the details about how to access this stuff vary between systems. And the dish tool I was initially talking about will generate some will generate the code that tells how to access stuff. So this varies a lot. I believe in Go 1.3 or sometime in the future there will be contiguous stacks, or I'd rather call them moving stacks. Stacks start up small, but when there's a need for growing the stack, the previous stack segment is copied into a larger stack segment, and the function return address is modified accordingly. So this depends on the precise garbage collection, because we need to change every point, all the pointers in the stack that were previously there. So we need type information to do that. We can't just consider everything a potential pointer. Go wants to own the signals. This is, I suppose, the primary problem. There are various people who want Go to run as a shared library, but the reality is that Go really needs to own the signals. So the runtime calls the necessary operating system functions that do signal stuff, and it implements an abstraction, so you can get a much nicer interface. The signaling stuff happens on a separate stack, the G signal. It uses the G signal. That's because, for example, in Unix, you can set up an alternate stack for signal handling, and Go use that. I think G signal is 32K. It's one G signal per M. Right. So the runtime can look at the state of the Go program, and it can generate stack traces. Of course, you notice that in Panix. But it's also used in profiling because profiling works by integrating signals, I think SIGPROF, with the ability to look inside the state. Yeah, the runtime does some more things, like I was saying, the deadlock detector and the race detector implemented in the runtime, but those are not really relevant for this talk, and these are fairly portable things. Yeah, yeah, this is not very important either. So, outside the runtime, the syscall package provides an interface to the operating system, and of course it varies between systems. However, there's some commonality on Unix, so this is really useful because, for example, the OS package kind of can use syscall, can have the same implementation for all Unixes. But of course, some details vary. For example, the networking, the network polar stuff depends highly on the system. So it's written in Go in assembly. There are Go functions, which about half of them are auto-generated by a Perl script. And these functions just call usually they call the indirect system call. The Perl script also generates constants and things like that, so we can know the trap numbers for the indirect system call. What's really important here is there's a syscall and the raw syscall. If you really look at the syscall package, the difference is that a regular syscall will inform the runtime that there's a syscall going on in order to potentially allocate a thread, one more thread, so it will not block the whole program. Raw syscall doesn't do that, which is useful for non-blocking syscalls and things like that. This distinction between integer types and unsafe pointers will be more relevant as the garbage collector will become more precise. I'm not really sure if the syscall code right now uses this correctly. I think it might use integers without having a reference to an unsafe pointer, but I'm not really sure. So the Perl stuff. Yeah, it's a Perl script. There are 3 variants now. There's also one for Windows. It looks inside the host headers to get up the constants and generate the types and all the things. You sort of can use it as a cross tool. It's a little bit trickier because you will have to provide all those headers, and you will probably have to modify things in order to use those headers, but you can do it. And this is really important if you can't get a CGO tool running on your target operating system. What's really important here is that most operating systems have in libc they expose the kernel interface, but it's really a shim, and they do some translation there. So for example, the trap numbers exposed by libc might be fake. So you really need as you are avoiding libc and you only interact with the kernel, you really need the kernel stuff. So on some systems you need to use the kernel headers. So Unix and Plan 9 calls the indirect system call. Actually, there are 3 indirect system calls depending on the number of parameters you use. Using the stuff we generated previously. This is okay because the system call interface is stable on most systems. Darwin is an exception. It's not officially stable and sometimes breaks, but for example, Linux is stable. Um there are some things that you lose by doing this, or I don't know if you lose, but you have to be aware of. For example, on most systems, when you do thread local storage, it's really a dance between libc and the kernel. Uh, so if that's the case and you don't have libc, that means that you don't really have TLS in the normal sense. So that means that if you want to use thread local storage for GNM, you need to implement this stuff on your own. I think most systems, there are system calls that you can use to do this stuff on your own. I mean, of course, libc has to have a way to do this thing. On some systems, this mechanism is portable, and some it's not. So you have to be aware of that. Yeah, Windows. Of course, this would be Solaris here. In Windows and Solaris, the system call interface is not stable. Actually, in Windows, it's pretty stable. In Solaris, it's not stable. I don't think Windows has this, but Solaris does have a indirect system call, but you can't use it because the trap numbers will change between versions. So you can't do the indirect system call. You have to use libc. We will take a look at how this is done. Basically uses some CGO stuff. It's not CGO per se as you regularly use CGO in Go. It's just some internal details that are used in here. So how this works. For example, if you really want to use symbols that are defined in a C object, you ask for the symbols, and then the generated machine code has to use those symbols in a way that the called code expects them to be used. I'm basically talking about the relocation mechanism here. In the most general case, ELF relocations are really complicated. So in the most general case, you need to have access to every object that you will be using in order to generate the most optimal relocation. This is done when you use the external linker. We unfortunately using the external linker means there's no cross compilation support, so we can't depend on anything that should be on the target system. So fortunately, there are some ELF relocations that we can do without having access to other objects. Unfortunately, those are the most slow ones. This is done by the runtime because the runtime really has to have some access to the system, but it really means that there can't be any lazy loading of functions and things like that. So, for example, the ports Windows and Solaris use some system calls like the thread functions, open read. They use this mechanism for that, but for all the others, they resort to deal open, deal sim, and basically using those functions to lazy load everything you might need. Because if you really you can do 300 system calls, you really don't want to for the dynamic loader to go through all this stuff and generate code for everything, except only when it's needed, because in practice you only need a small subset of system calls. As I was saying, in the differences between the syscall and raw syscall, a syscall notifies the runtime by calling enter syscall. This is a function defined in the runtime package. So this is it does what you expect. It put there's the G there are the G state transition is like in a regular operating system, like the runnable running things like that. There's also a syscall state, um, and when it's in this state, it means that it owns the thread it's running on. So the runtime might allocate or might allocate more threads for other things to run. There's a thread limit, I suppose. I think it's 10,000 threads right now. It's you can change it. There's a something in the runtime, like set max threads, I suppose. You can change that. Um, right. So the network package. For example, the OS package, the extraction Go provides is pretty close to what the operating system provides. Like file descriptors and doing read and writes. For networking, is slightly higher up the stack. Of course, it uses Berkeley sockets and using Windows and something else on Plan 9. You have to be aware of the fact that by default it wants to use CGO to do name resolution, but you can disable that. But well, of course, one way is by disabling CGO. But if you're compiling natively, there's and you still want CGO, there's some build type to disable that. Without CGO, it will resort to doing DNS and local queries for this stuff. So it kind of works really. What's more important here is how the network pooling mechanism works. So you want to have a poller for networking, because as I was saying, otherwise you'd have a thread per each system call. So for each connection you'd have a thread, and if you want to avoid that stuff, so by doing I/O multiplexing of some sorts, you can have a system where you only need as many threads as many things do I/O at a time. So the way this works is by the network package doesn't do read and writes and things like that. It calls the network poller, which is implemented in the runtime, and the poller will use some mechanism, for example, KQ or ePoll or things like that, in order to do I/O only when it needs to. Actually, I think this was previously done only in the network package, but it was moved inside the runtime because the poller knows which coroutine needs to do I/O. It can be integrated with the scheduler so that it will schedule that particular coroutine. One note: the poller requires edge triggered I/O, so select is out. Right, so now moving on to actually porting Go. So first you have to add a new GoOS, and this is easy stuff. Add it inside CMD dist, Go build, everywhere. You can basically grep for some other GoOS and add it there. One note: there are two ways of doing this. You can start by cross compilation, and always do cross compilation. Basically, we didn't do that. I suppose it's for Go for some other things. I suppose it makes more sense. But Go, the dependencies it has, like the CGO, this tool is like a very small C program, and I think it's really worth it to do it natively. One more note: we did this, and it paid a lot. Is to really use the stuff you're hacking on. I mean, before the Solaris port worked at all, I used the same tree on my Linux and BSDs and every machine I had. So I always made sure I never broke the tree and never broke any kind of other assumption. And Otherwise, you will break things and you will not even know. And this is not hard to do at all, really. Right. So right now, I've add your operating system wherever it's needed. I think right now it's needed in compilers as well, because the compilers use liblink, which is the linker stuff factored out as a library. But this will take 1 hour, I suppose. Okay. Right now, so you really need to understand the binary format you're targeting. That means you should look at objects using whatever tools you like, because you really need to understand the differences between what should be and what really happens. So take a look at. I suppose most operating systems will have a stable ABI, and you will use you will do system calls for each. So just use very small programs that don't use libc for that system, and take a look at how they do. How take a look at the object, what relocations are inside the event, how these things happen. So when you're adding stuff to the linker, you can always grep for other systems. The linker is pretty hairy, I suppose. Lots of special cases for lots of operating systems and things like that. You should grep for popular stuff like Linux, and also non-popular stuff, because Linux has all kind of special code to make things faster, I suppose. Other systems don't. On the other hand, other systems do have special codes to do their thing, but you see why isn't Linux doing this thing as well? So you need to take a look at all of those, and you need to be aware of what your system requires. Okay. Some notes for Solaris. There are no static binaries on Solaris. I suppose it's to be expected since you are required to use libc. But when I mean there are no static binaries, I mean they really don't, for 64-bit they don't run at all. Other systems may be similar or not. So yeah, if you use ELF, I think you're pretty much covered. If you don't use ELF, but if you use a.out, you're pretty much covered as well. But otherwise, you have to really be aware of the binary formats. The first thing that you need to do is write some hello world programs in assembly. This will accustom you to the calling convention necessary, and you need to know how to do a system call. But what's really important is that you need to do the same with the Go assemblers as well. And when you try to do this, you will have some problems at first. For example, you link the runtime, which obviously doesn't work yet. You can use CMD pack to extract the startup object, and you can insert your own startup object, and essentially you avoid the runtime completely. Of course, everything you do right now has to not split the stack. There's this flag that can be used in the assembly, because if you split the stack, it will try to access the runtime, which doesn't work yet. There's no G, for example, right now. Once you have something working, you should do the same in C. You might need to disable dwarf. I know that we did need to disable dwarf for some time. I can't remember why though. Right. So the thing with C is that since the C compilers kind of uses the same calling convention as the Go compilers, this is the place where you will learn to do the ABI translation between the calling convention of Go and your target operating system. And this is really just hello world level thing, so this is really easy to learn things at this level. So you should use pack to create an alternative runtime. We called ours alt. And you should create some test infrastructure that builds things using this alt runtime. This will be very useful because you will can write tests and things like that, and will be very useful in the future as things break as well. So, as you probably when you will try to use the linker for the first time, nothing will work because all kind of symbols will be missing. So, most signals that will be missing are inside the OS file, OS specific file, and all kind of symbols here. And this file, about half of it, I suppose, is really sort of common between systems. Another half is not common at all. For now, you just need stubs. You don't need to do any kind of implementation at this time. When you try to implement things, you should start with, of course, obvious things like file I/O. But then you need to decide. You need to find out what's the best way of creating kernel threads. libc usually exposes POSIX threads, but you might not want to use POSIX threads. You might want to use the actual native threads the kernel is using. For example, in Linux, the Go runtime uses the clone system call to create threads. There are similar calls for other systems. As a note, for Solaris, we do use POSIX threads because we really are using libc. Solaris has two kinds of threads. The POSIX threads are a very thin layer of native Solaris threads. We decided to use POSIX threads because we thought it might be useful for other ports in the future. That doesn't really matter much. What matters, the synchronization primitives the operating system gives you in order to do synchronization between these threads. Again, there are POSIX locks and things like that which you might want to avoid. Yeah.
How far are you from this?
Sorry?
How far are you through this one?
I think I'm about 2/3, but I think my time is out, I suppose. About half.
Oh, wow.
No. But I can stop.
Yeah. Can you make the slides available somewhere?
Sure,
the notes?
sure, obviously.
I certainly, you're the only person who's documented this process.
Yeah, surely,
So,
obviously.
so that would be great.
Yeah, surely.
I guess if you have questions for Aram, we should get you to ask them outside or by email or something. We need to get on with the lightning talks. But thank you very much to Aram for this. Maybe just while he unplugs, you can answer one or two questions if there's someone who has anything.
Right.
Is there a plan to port Go to Spark Solaris?
Well, that would require writing a Spark compiler, basically.
Yes.
There is no plan, but I have no plan. Anyone can have plans. I don't know.